I am Banshi from NCRA, and so as we know that the FRB progenitor is not known yet, and there is Magnetar is one of the leading candidates for FRB. But except for FRB-like event from the galactic Magnetar, we are not seeing very energetic burst from the Magnetars. So here I am trying to see the low energy radio emission from one Magnetar, J1810-197. I am studying this low energy radio burst to investigate the Magnetar FRB link. And so Magnetars are basically young neutron stars with very high magnetic field, and they are slowly rotate compared to the pulsars. So their emitted energy is not explained by the rotational energy loss. So these are powered by decay of their internal magnetic field, and magnetic field can increase the crustal stress, and that releases in the form of sudden fractures in the Magnetar crust, which are like star quake-like situation. And so yeah, magnetars are mostly detected via their high energy emission in X-ray, and they are two kind of sources: persist and transient sources. And transient sources detected during the outburst, and one of such transient source is J1810-197, and this is the magnetars Pulak also talked about. And so magnetars give different kind of emissions, like short duration emission, which lasts typically less than a second, and outburst, which is sudden enhancement in the flux with very long decay time. And magnetars also give giant flares, which is sudden release of enormous energy. And during an outburst, magnetars can collectively release energy which is compared to the FRBs. So yeah. For FRB progenitor, there are many theories listed in this FRB theory cat, and they say they include different progenitors, the different theories, including neutron stars like pulsar magnetars, black hole, AGN, and white dwarf. And many of these theories propose Magnetar as the progenitor for the FRBs. So, and this a strong evidence of Magnetar as progenitor comes in April 2020, when we detected an FRB-like event from the galactic Magnetar SGR 1935. So during this event, Chime and Steer 2 simultaneously detected a very bright burst at L-band and and also at the Chime with up to with 1.5 mega Jansky millisecond fluence, and which suggests that at least some of the FRBs are originated from magnetars. And except this event, as I mentioned earlier, magnetars normally give fluence of a few Jansky millisecond, not very high. So here I am studying this low energy burst from this particular magnetar J1810-197. So this was discovered during an outburst in X-ray in 2004, and this is the first ever magnetar which was also detected in radio. And then the flux density decreased with time, and it became undetectable in 2008. Then it again detected during another outburst in 2018. And since then it is followed by different telescope across the globe. So here I am using data set from GMRT and GBT. So here I am using very long monitoring from December 2018 to almost August 2023. And this data set is covering a huge frequency range from 300 to 6,000 megahertz. And we have more than 240 observations with the on-source time of around 140 hours. And we have detected around 100,000 single pulses above 13 sigma level. And for each of these observations, I have computed the fluence and fluence distribution for all the pulses. And so here are some distributions. So we had noticed that the magnetar state changes with time, and its fluence distribution also changes with time. So some of examples are shown here, like power law, then log normal distribution, and broken power law. So we have fitted all the distribution with 4 different models: power law, broken power law, log normal power law, and modified log normal power law, which is mixture of power law and log normal distribution. So after characterizing the fluence distribution, I have done So from the fluence distribution, we can get the rate function for a given observation, and we can extrapolate that rate function up to a very high fluence, and the inverse of that rate function gives us the time scale expected time scale to detect at least one pulse of that very high fluence. And I have computed the expected time scale for a fluence of 1.5 megajansky millisecond. So I have chosen this value because for this fluence, the energetics are comparable to the FRBs. So here is the plot of the time scale. So so here on the x-axis is the observation date in MJD as shown, and y-axis the time in the expected time scale in the years is shown, and different colors here represents the different frequency band, and different indices represents this different model which are fitted the closed circle, the field circles are represent broken power law. Open squares are like this. These are log normal distribution, and the filled squares are modified log normal power law. So here we can see that there are, also here I have only listed the values which are less than 10 for 5 years. At the initial stage, there is no point because all the expected time scale was very high compared to the 10 for 5, and then around 2019, mid of 2019, the expected time scale start decreasing, and it decreased till around mid of 2021 or so. So here as the emission state of Magnetar evolves, its fluence distribution evolves, and that is also reflected in the time scale. And if the Magnetar have continued to evolve in the fashion that it has done here, then the expected time scale might have been even lower. And one more thing I would like to mention here. So for the shorter time scale, these are either fitted with broken power law or modified log normal power law, which suggests that the power law, the distribution tail is always fitted by the power law in both the cases, in broken power law and modified log normal power law. And we had seen in the pulsars that the giant pulses follows the power law. So from here we can say that the FRBs can be giant pulses from the magnetars. And I have also computed the time scale for Crab pulsar. So I have used this power law index of 2.8, and this gives me the time scale of few hundred years. And but for the Magnetar case, the emission state itself changes with time, so that the power law changes with time, and the expected time scale changes. But for Crab pulsar, the power law index doesn't change much. I have listed a few values here. Across these are reported at different times and different frequency. So from here we can see that it doesn't change much. It is 2.8 and plus minus 0.5 or something like that. So the expected time scale doesn't changes with time much. And also because the Crab pulsar has a low magnetic field compared to the Magnetars, the energy budget is also low for Crab pulsar. So for Crab pulsar, it is highly unlikely to give an FRB like burst. And one more thing, that FRB fluence is also follows the power law like 12.1102. So from here I can say that the FRB could be giant pulses in their from magnetars in their favorable emission state, when the distribution fluence distribution tail become shallower. And so another thing I have done is looking at the waiting time distribution using all the pulses. So here we can see that there are two clusters in the waiting time distribution. So here on the x-axis is the waiting time, and on y-axis the number of pulses. This is histogram. And so here we can see that the first cluster peaks around 100 millisecond or so, and there is another cluster. So this second cluster is due to the spin period of the Magnetar and its harmonics. And if we look at the pulses with high fluence greater than 100 Jansky millisecond, which are represented in these red lines here, the two clusters are prominently different, and and also in FRB shows the similar bimodal distribution for the waiting time, like these two FRB I have listed here. So in FRBs also, the first cluster peaks around few tenths or millisecond order, and the second cluster has few tenths of seconds or so. And and also in one of our observation, we have detected around 130 pulses with fluence greater than 100 Jansky millisecond, and with a rate of around 197 pulses per hour. And so here it is shown. So I have plotted the pulse arrival time in spin phase of the magnetar. So here the histogram is shown. Here we can see that these pulses are gives a very narrow distribution in the spin phase. And using the Lom's-Cargill periodogram, I have tried to compute the periodicity for these arrival times. And we can see that there are peaks at the pulsar at the magnetar period and its harmonics. So then I have done that manually. I have widened this distribution in spin phase, and try to compute the widen this distribution, get arrival times, and try to again search for the periodicity. And I had seen that when the distribution is widened in the spin phase, the significance of these peaks are decreases. Like here only we see at one peak only at the period of the magnetar, and around if the spread in spin phase is around or greater than 60%, we are seeing almost no peak there. So FRBs might be emitted over very large range in the spin phase, so that their periodicity is not detectable. And also this wide range of emission in the spin phase is not very common, but there are many sources like pulsar and this magnetar which shows the wide emission range in the spin phase. So yeah. So right now we are in the future direction. We are looking at the starquake and magnetar emission. So as I mentioned in the introduction, that the explosive phenomena triggered by starquake in the magnetar crust. So in starquake-like situations, the bursts are not correlated, not just consecutive, but beyond the consecutive pulses, there is some correlation, and this correlation is given by the number of excess number of pairs over an uncorrelated case. And there are studies for magnetars and earthquakes. These are compared, and the similarities has been found in the literature. And recent study shows that FRB also shows the similar correlation as the earthquake. So this is the plot. So here I am. This is ongoing work, and I am showing for one of our observation. So here the first plot is the. So for all the observation, I have computed the time pair and corresponding energy pair. So here it is showing the distribution. The second plot is just the density plot of these pairs, and I have generated the random pairs at the period grid of the magnetars using some emission window. And for this, this is the density plot is shown, and the fourth plot, this bottom right is represents the 2-point correlation function. So here we can see that at shorter time scale we see some strong correlation, where at the longer time scale there is almost no correlation. And also at the shorter time scale the correlation is present in time and energy. And if we look at only the time axis, on the energy axis the correlation doesn't change much, but on the time axis it is changing. So it seems like the correlation is more prominent across the time axis compared to the energy. So we will do only the 1D correlation for the time, and we will do this for all the observations, and we will try to look also collectively how it is changing with time, and also over the frequencies. So yeah, here is the conclusion. So So Magnetar's emission state changes with time and frequency, and Magnetar's could emit FRB like burst in reasonably short time scale in many emission state. And FRB like emission could be giant pulses from Magnetar, but it is highly unlikely from crab-like pulsar. And the bright pulses shows the waiting time distribution, which is similar to FRBs. And non-detection of periodicity in the repeating FRB might be due to their arrival time spans a larger range in the spin phase. Thank you.
Thank you, Bansh. Any question? So I'm sorry, but just a quick question is that could you explain why the crab-like pulsars are unlikely for the FRB emission,
Yeah.
but Magnetar should be?
So from here we can see that Magnetar emission state changes with time. So the expected time scale changes with time. So Magnetar can go into a favorable state while evolving, where the time scale is very shorter. While for crab-like pulsar, the distribution itself doesn't change with time. So the expected time scale doesn't change with time. So it will remain, I mean, more or less few hundred years whenever we observe it in an emission state, I mean, over the time.
Does it imply that the giant pulse, the mechanism for the giant pulse is different from the magnetars and the crab-like pulsars, are you saying?
Yeah, it seems they are different because in the Magnetars, this is mostly powered by the magnetic field, and there might be happens like a starquake and this thing that can trigger to a different emission.
You see. Thank you. Any other question? Okay. Sorry. Online. I think we can discuss more offline because we are running out of the time. So let's thank our speaker, Banshi, again. Thank you.